Let's start. So welcome. Last time we started on these circular motion notes and we talked about various aspects of it. We're going to talk about uniform circular motion, which is a particle or a mass going in a circle at a steady speed. And we find that very important because, first of all, it does happen in nature, but secondly, because it gives us a mathematics which will help us with a thing called simple harmonic motion, which is an oscillation, which we'll do a lot of in physics too. So we're laying some of the foundations for that. And then secondly, we have non-uniform circular motion, where you actually speed up and you slow down, and we need to deal with that. In the middle, there are four classic examples of uniform circular motion, and we'll do a couple of them today. All of them are on the website. If you go to the YouTube channel, I've worked out all the examples there, so you have them. Last time we kind of used this expression, this construction really, to prove to ourselves that there was this circular motion, that there was this centripetal acceleration. Let me get a pen up and we'll get going. So we have this pen up, yes. So there is this centripetal acceleration, and it points towards the center of the rotation. You don't go in a circle without it because you need an acceleration to change your direction. And you don't get an acceleration without a net force, so you need a force from somewhere. And the net force comes from the physical system. And there's this, and I remember making this mistake when I was a student. There's this tendency to think that because you are going in a circle, there must be this thing called the centripetal force. And so you add it to your other forces, when in fact the centripetal force, if you want to use that term, is a debt. It's like, I need to get this amount of newtons from one of these other forces. And the analogy I made was, you know, if you go on vacation, they don't give you money because you go on vacation. You need money to go on vacation. So you need a force of some kind to cause this circular motion. And it could be the gravity of the Earth pulling on the moon, could be the tension in a string, could be friction in tires, could be a component of the normal force on a bank track. In either case, in all cases, some force must be pointing towards the center of your circular motion, and that is paying for your circular motion. I brought out of hat, I'm not justified it, that the centripetal acceleration is equal to v squared over r. And I think we got as far as this, didn't we? We started talking about these. Tip number one. Irrespective of how I draw my drawing, my advice is you put the mass, when you look, so you're going to look down from above, and you're going to see the circular motion. And you're going to recognize in there that there's a centripetal acceleration, which must point towards the middle, and there's a tangential speed, which is tangential, and there's going to be a mass. And then basically all we're doing is applying Newton's laws. This is just Newton's laws work. Just Newton's second law. You're going to say, well, let's look from the side. And I want you to, you don't have to, but I think it's easier if you always draw your mass over to the left-hand side. Because that then means that your tension force in this case is pointing in a positive direction, as is your centripetal acceleration. If you happen to draw it in the other direction, then your forces are negative. And if you're careful about your signs, it'll make it harder for you. If you're not careful about your signs, then you'll get away with it. But I want you to be careful about your signs. So watch out for that. So I might draw it with the mass over here, but you know, when you draw it that way. So consider a ball of mass m tethered, that means tied to some pivot point by a length of string r. The ball travels in a circle with a speed v. The ball experiences a centripetal acceleration that points towards the center of the circle. That's the way it works. The acceleration is caused by the tension provided by the string. Without that tension, you don't go in a circle. You're going to continue in a straight line. And the two equations that come to mind are my centripetal acceleration equals v squared over r, and Newton's law, F equals ma. There's an acceleration, so F equals ma. There are 4 classic examples, and you can bet on getting one of them, at least. And so this is the so-called soap on a rope. It's basically a mass that's tethered by a piece of string to some kind of axis. Typically called soap on a rope because back in the 70s there was this Christmas or winter holiday dilemma of what do you buy for your mom, I mean, what do you buy for her? Does she read books? I have no idea. She's my mom. Does she cook? Well, yeah, but she don't want that for Christmas. What do I buy for her, So you're hunting around trying to buy her something, and then somewhere, like it's not Bed Bath & Beyond, but it's someone like that in Britain, brought out soap on a rope, and it went among all your classmates. Buy your mom soap on a rope. What is it? It's like a piece of rope with a piece of soap stuck to the end of it. Why? So when you're in the shower, you don't drop it. You can just But we don't have a shower. We don't have a shower. Well, don't worry about it. Just buy her it. She'll like it. So we buy her it, and she goes, what's this? And you go, it's a soap on a rope. The following year, the big thing was bath salts. For some reason, my mom, one holiday, from everybody in the family, including me, got bath salts. And as she's opening up the packages, and the first year, bath salts. And then it's like, bath salts. And then it's like, bath salts again. And you know that your present is bath salts. It's just going to get worse. But you don't know. You're looking at your brother like, did you buy bath salts? He's not making eye contact. And in the end, your mum goes, are you guys trying to tell me something? And he's like, no, we're just like thoughtless children, we just, hey, it's the easiest present out. So soap on a rope is just a piece of string with a mass attached to the end. The next one is, and that's relatively straightforward, by the way. The next one is a little bit more interesting. Here, the centripetal acceleration is paid for by a frictional force. So we have a car literally going around a circular track, but it's not banked. And so then we come to our third example, which is so-called conical pendulum. It's like soap on a rope, but it's basically you're not trying to keep it horizontal. So there's your tension, but it's at an angle to the centripetal acceleration. So you're going to take the component of tension pointing towards the centripetal acceleration, pointing towards the center of the circle. And then the last one is we have, a normal force. We have a bank track. And again, we've always got to use the sum of the forces horizontally equals ma. So remember, you always go in the direction of the acceleration. And you say the sum of the forces equals ma. Well, in every case, the centripetal acceleration is pointing towards the middle or the axis of the circle. And so you have to take the component of the force that's in line with that if the force itself is not in line with that. So the tension is in line with it and the friction is in line with it. But in this case, you've got to take the component of the tension that's horizontal. And in this case, we take the component of the normal force that's horizontal. But in every case, the approach is the same. In every case, the approach is the same. You're going to say the acceleration is towards the center of the circle. So the sum of the forces equals ma towards the center of the circle, and the acceleration is v squared over r. Then you just do Newton's laws problem.
So that red arrow, that's the centripetal acceleration?
Which red arrow?
And
this guy down here?
No, to the right.
This guy here? No, this is the component. Well, it could be either, but I'm drawing it as the component Fn in the x direction, if you like, yeah. So, let's do an example. A 2-kilogram ball is attached to the end of a 4-meter long rope. The ball moves in a horizontal plane. That's hard to do, actually, so sometimes you put it on a frictionless table. It's actually hard to do, actually, in practice. The string can withstand a tension of 80 newtons before it breaks. What is the maximum speed the ball can attain before the string breaks? So here's the mass, that's 2. Here's our string, there's our tension. I can't really draw this very well, but I'm going to have my V, my tangential speed, is going to be what I want. That's what I'm trying to find. So let's just draw this as a... And let's have a look. This is 4 meters radius from there to there. And we have other forces. We have a downwards force, and we're not going to talk about that though because it's perpendicular to our direction of travel. And I'm going to say, is there an acceleration? And there is. There's an AC. So I'm going to say, find T. T is horizontal using hor info. That takes us back a bit, doesn't it? We know AC equals V squared over R. I know that much. I'm actually putting down the whole things that I don't know the answer to. So let's just say find T using horizontal information, using the sum of the forces horizontally is equal to the mass times the acceleration horizontal. So I'm going to say the sum of the forces horizontal is equal to MA horizontal, which equals MAC, because AC is horizontal, which equals MV squared over R. So I use Newton's first law, the sum of the forces equals MA, and I use the centripetal acceleration, AC equals V squared over R. So those were the 2 equations that I used. Now I look at my diagram and I say, well, there's only one tension horizontal, and that's T max. It's asking us about when the tension is maxed out. T max equals 80. So that's going to be plus 80. There's nothing dragging back in the other direction, so that's just plus 80. Is equal to the mass of this thing, which is 2, times the speed of this thing, which is what I want, over the radius of this thing, which is 4.
So the Tmax is going to be the horizontal force?
It says, what is the maximum speed the ball can attain before the string breaks? And the string has a horizontal force in it, which is tension. The maximum speed will occur when you have the maximum tension, so Tmax, horizontal force. So I'm looking at my diagram, and I'm saying, what force is horizontal? It's T. Let's put it in our equation. What acceleration is horizontal? Put it in our equation. What's the mass? So this gives us that V squared is equal to plus 80 times 4 over 2, which equals plus 160. So V is equal to the square root of 160, which equals, pardon? 12.65. And it's going to be meters per second. So not so bad. We just drew a good diagram and we applied Newton's second law. And we used this little bit of information that centripetal acceleration equals V squared over R. Questions? I'm not going to get time to have you do one because we're just going to be buried. So let's just move on. 6 kilogram car moving on a flat horizontal track makes a turn of 2 meters radius. A 0.8 coefficient of static friction exists between the tires and the track. What is the maximum speed? So very similar. Let's draw a diagram. Here's our car. There is a force of friction. The force of friction is in the opposite, in the direction which tends to oppose the tendency to motion. Looking from above, this thing does not want to go in a circular path. It wants to actually go in that direction, wants to effectively move away from the center of the circle, so our force of friction is going to be towards the center of the circle. That's not so easy to justify, but your tendency is to radially move away. It's not actually radially moving away, it's just getting further away from the center. So my force of friction is in that direction. Well, that's towards the center. I'm going to put the center over here because I don't want negative stuff on there, so that's going to be FF. And let's have a look. This is going to be our radius, and our radius is 2 meters, pretty sharp turn. And we have 6 kilograms. Okay. I say the sum of the forces horizontally equals MA, which equals MAC, because there's only one acceleration, AC, which equals mv squared over r. Okay. What do I know? Sum of the forces horizontally. Oh, hold on. I can find that. So I come down over here, and I go FF. I go, if this is 6, can I write down 60 down for the weight? Are you okay with that? And because it's on a horizontal surface, can I write down 60 for the normal force? I'm going to put them in so we know what they are. This is FG.
Would FG be negative?
Well, it's pointing downwards. The arrow's pointing downwards. So if I was to use it in an equation, I would call it a negative FG, yeah. And I know that FF is equal to minus mu, is equal to mu Fn. So I know that FF is equal to 0.8, because that was my mu, times 20, which equals, what's that going to be, 16? Yeah? Am I right?
You're assuming an acceleration of gravity there.
I'm assuming that the force, the gravitational field strength, little g, equals 10 newtons per kilogram. And so if I want to find this weight, I say weight is equal to mg. That is the g. I know that you probably... Oh, so yeah, the car is moving in a horizontal plane, but it still has weight. Agreed? Yes. And the way I find the weight is I use mg, but g is not the acceleration due to gravity. I know most people were taught that. It's a really bad thing to be taught. It is the gravitational field strength. It's just the pull of the earth on the car, and that's going to be 10 newtons per kilogram. Yep.
I thought the normal force was 60.
Yeah, why should you put 20?
Oh, because I messed up. Sorry. So completely messed up. Okay. So 6/8 of 48. So that's 48 newtons. Is that right? Yeah. I thought there was silence when I said it. You know, it's like. So sorry about that. I don't know where that came from. So okay, that's 48 newtons. So we say that plus 48 is equal to m, which is 6 times v squared, which is what I want to find, isn't it? What's the speed? Yeah, v squared over the radius, which is 2. So v squared is equal to 48 times 2 over 6. So v squared is equal to, well, let's have a look, 6/8 of 48, I guess. So that's 8 times 2. That's 16.
Yeah.
So v is equal to 4 meters per second. Cool. So can you see? It's the same problem. It's just with a little wrinkle on the side, yeah. But it's the same problem. It's just with this little bit about. The finding the frictional force, and that's the pattern we're going to see on all of these. It's just using Newton's second law with a little bit added. So let's do the next one. Oh, and again, I don't have time to go through that, so I'll go through this with you. A 6 kilogram ball is attached to the end of a long string. The ball revolves with a constant speed of 3 meters per second in a 4 meter radius horizontal circle. That forms a conical pendulum. Find the angle that the string makes to the horizontal. So this is a little bit harder for a number of reasons. I'm not asking you for the velocity again. I'm asking you to find an angle, and so it's just always a little bit more awkward. And this is where a good diagram helps. And again, I'm going to draw my diagram with the mass over to the left-hand side so that my centripetal acceleration is positive. And I'm going to have, this is going to be, I'm going to draw this there. And there's my tension. And this is theta. And then I have a AC in that direction, and I have 6 kilograms there, which is my mass. Oh, I'm sorry, I need to just I want to modify my thing ever so slightly. I'm going to put that, there. I'm going to put my AC kind of like here, because I don't want it to get in the way down here. Where is the acceleration? The acceleration is horizontal. The sum of the forces horizontally equals ma, which equals m centripetal A, which equals mv squared over r. Okay. Got to think in terms of components now. So let's come along here. Let's change color pen so you can actually see, you know, the different thinking bits. So here I am, and I'm thinking about this, and this guy here is going to be t cosine theta. Agreed?
Yeah.
It's the horizontal component, so it's t cosine theta. So I'm going to say, oh, t cosine theta. There is a 60 degrees down, 60 newtons down there. But if I resolve my forces horizontally, that has no component. Yeah? So t cosine theta is equal to the mass, which is 6, times v squared, which is 3 squared, over r, and r is 4. Okay. 2 unknowns. That's a bit of a problem, isn't it? I don't know t, and I don't know theta. I want to find theta. Couldn't find t horizontally, so yes?
How's that t cosine theta different from the red line that's right above the AC?
I mean the dotted red line.
Yeah.
The dotted red line is just showing me my axes. It's the green arrow is a vector because it has an arrowhead on it, and it is a line that looks like an arrow. And in my thinking, I drew the dotted red line to show you a horizontal axis, and the dotted vertical line to show you the vertical axis. So I'm representing different things by those two different lines. Yeah, okay, but it's in the same direction. Yeah, for sure. So, and it's important, actually, that raises an issue. Supposing I had given you the length of the string, and I'd given you the radius, you'd know theta. But that doesn't mean to say that and I could work out the length of, if I had the length of the string, that doesn't mean to say that that is the size of my force. And sometimes people see an arrow for the force, and they say, oh, it's a 6 meter long piece of string, and then they say, oh, well, that means that that arrow must be 6 units long, and now it becomes 6 newtons. It's just in the same direction as the piece of string. The tension is just in the same direction as the piece of string, because that's the way strings work. So then I turn around and say, okay, well, I'm going to do a bit more work on this thing, so let's go to a different color so you can see the bit more work. And I'm going to say, oh, well, I tried horizontal. We always learn to go the opposite direction, you know, orthogonally, so the sum of the forces vertically equal what? Apply Newton's second law Applying Newton's laws vertically. Sum of the forces vertically equals 0. Why 0? Because it's not accelerating, is it? It's not. This bob is not speeding up. It's not speeding down. It's not slowing down going up. It's not slowing down going down. It's not going up or down. It's stationary in the vertical. So it's in equilibrium vertically. And now I've gone and, messed myself up because now I put my t cosine theta right where I didn't want it. So I can do this in black and you'll forgive me for that. And this guy here would be t sine theta. Yeah, because it's, t's the hypotenuse and I want to use the opposite over the hypotenuse, which is a sine. So I'm going to turn around and say, okay, vertically, I'm going to say plus t sine theta added to minus 60 is equal to 0. So t sine theta is equal to 60. Okay, so I got two choices now. I can be kind of cute or I can be kind of straightforward. So let me show you the straightforward way. Straightforward way is I want to get rid of that t. So I'm going to turn around and say t is equal to 60 over sine theta. And then I substitute that in there. So I say 60 over sine theta times cosine theta is equal to, we can do some math over here, 1.5 times 9 is 13.5. Yeah, 13.5. Okay, so then, what's a cosine theta over a sine theta?
No, cotangent theta.
So, I don't know cotangents. What is that in terms of sine, coses, or? 1 over tangent, isn't it? Yeah, let's keep life simple. 1 over tan theta is equal to 13.5 over 60. Did I do that right? I think so. So tan theta is equal to 60 over 13.5. So theta equals tan to the minus 1. Did I bring am I a physics person? Yes! Brought my calculator today. Good guy. So that's going to be second tangent, 60 divided by 13.5. And that's going to be 77 degrees. 0.3 degrees. Yeah, it's actually one of the answers. Pretty close anyway. 77.3 degrees. So that's that kind of straightforward way. Did I do it right? Did I do that right? Am I in radians? I hope I'm not in radians. No. Agreed? I'm getting no response. Agreed? Yeah, good. So let me show you the cute way. It's just a little cute thing. It's kind of like I don't really care about it, but you'll see it sometimes and you go, where did that come from? So what I could do is I could say, oh look, a t cosine theta and a t sine theta. So I go, oh, I know what to do. I'm going to say t sine theta over t cosine theta is, well, t sine theta was 60 over cosine theta, I got to work that out, 13.5. Oh, look, tan theta is equal to 60 over 13.5. Theta is equal to 77.3 degrees. And I kind of like it because it's cleaner, and I dislike it because it's not obvious unless you see this thing that's not mathematically necessarily the next step. It's like a trick. It's a nice trick. It's it's nice to play with math, so you get really comfortable with it. It's like, doing a special kind of basketball throw that's not obvious, but you kind of learn how to do it. You know, one of those hook shots. Somebody invented it, and they said, "Oh, look, I can do this." You could always do it, but it took somebody to invent it and say, "Look, it's kind of useful." It's a bit like that, where it's kind of you don't need to know it this way mathematically. If you had a computer doing this, probably wouldn't recognize that this is a shortcut, but it's a shortcut. So don't get tied up in the shortcut. Don't worry because you didn't see the shortcut. That comes with just practice, you know. So a little bit harder. I could have asked this same question, given you the angle and asking you for the velocity like I did the previous ones. I just gave you a little bit of a harder question because it's not obvious. It's not so obvious where you begin. If you're focused on the angle, how do I begin? How do I begin? No. You begin by saying there's an acceleration. Apply Newton's second law in line with that acceleration. Can I solve it? No, I can't. Apply Newton's law perpendicular. Oh, it's Newton's first law perpendicular. 2 equations, 2 unknowns. I'm done. It's the same pattern we've done over and over again. If you see an acceleration, Newton's second law in line with it. If you can't solve it, go perpendicular and it will be in equilibrium. That's the same pattern. Just happens to be a circular motion bed. So this last one, actually doing all of them. I didn't think I'd do all of them, but you know, we'll see. I might run out of time. We'll see. A 4-kilogram car moves on a bank track that has a radius of 5 meters. The banking is designed so that the car does not rely upon static friction when traveling at optimum speed. They actually do this in roads. I noticed it. I was taking my daughter home one time, and I thought she'd passed out. It was like she was in the like kid's seat in the back, and I looked in the mirror and I could see she'd pulled the blanket down over her head, and I thought, oh, she's gone to sleep, and then I thought, oh no, yeah, I'm always I'm an optimist with a really pessimistic heart, and I'm going, oh no, she's passed out. Why would I think that? And I started calling her name, Emily, Emily, no response. I reached back while I'm driving on 275. I reached back and I'm like shaking her leg to try and rouse her. No response. It suddenly dawns on me, this is an emergency. Stuff like this happens. So I'm fighting my way onto the hard shoulder. And I remember I had my indicator on. It's one of these weird situations. I had my indicator on and I remember thinking, this is an emergency, and I'm like doing all the niceties, you know? Get over there. And I kind of forced my way into the hard shoulder, and I remember I braked on the gravel because it was pretty dirty on the hard shoulder. I braked on the gravel, and my car kind of like screeched to a halt, and I jumped up, and I got hold of her, and as I pulled the blanket back, she just started laughing. And I wasn't sure, to this day I'm not sure, if she had fallen asleep and I woke her up, or whether she was kind of playing peekaboo with me. I have no idea if she did it on purpose, because we do the peekaboo stuff all the time. So my heart was like racing, and the adrenaline, you know, it's like when the adrenaline's kind of like gone, you know, I feel it. And I go to get back in the driver's seat, and it's like, I'm at this like huge angle, and it's like, man, this is really steep, you know. And I get back in the car, and I'm like leaning against the car door as I'm trying to get the thing in gear and get on before it's 275. These cars are flying by. It was like I waited a long time for a gap, because that's the last thing I wanted was, you know, oh, she's fine, but now you have a crash kind of thing. And it struck me so much, I went back, like a couple of days later, went underneath 75, where sometimes you can go underneath it and you can see the banking, and the banking is really quite steep. And they do it so that you don't have to turn the steering wheel to go around the corner. You just like keep going straight, and it takes you around the corner. On an interstate, so I had a student in my class who worked for the DOT, and he brought me in the plans, and it's like there's all these codes for if the speed limit is this is what you bank the corner at if you're going to go through so many degrees. It's all worked out so that if you're doing about the speed limit, you're doing, you know, typical traffic speed on an interstate, you don't have to touch the wheel at all. It's like the most amazing thing. So this is done all the time. A car moves on a banked circular track. So little car, let's do it like that. There is an acceleration. So we're going to have our acceleration, the AC. There is a weight. That is going to be 40 newtons, and there is a normal force, Fn. So that's basically the information I have. And what do I say? I say the sum of the forces horizontally is equal to MA, which equals MAC, because it's still centripetal, which equals mv squared over r. And in this case, optimum speed, I'm trying to find v. Oh, this is not so bad then. So this banking is at 20 degrees. So what that means is that angle there is 20. Okay. So let's change colored pens so you can see the thinking I'm doing. So we're going to go to colored pens. Let's go back to green. So I come along here and I want to resolve my forces horizontally, and there's my horizontal force. And this is going to be Fn. Now, if this is cosine 20, then this is 20. This is 20, that's 70, 70, 20, 20, 70. So 70 is in here and 20 is up there. It's up to me which one I use. I'm going to say it's Fn cosine 70, just for the sake of it. Does everybody see where that angle comes from? I have a little angle, which makes a big angle, because they have to add up to 90. I have a little angle, because those two add up to 90. I have a big angle, because those two have to add up to 90. Can you see that? And also you can see it from the diagram. There's a little and big angle. I'm clearly talking about the big angle there. Okay, so then I turn around and say, okay, well, plus Fn cosine 70 is equal to my mass, which is 4, times my v squared, which is what I want, over my radius, which is 5. So my v squared is equal to 5 over 4 Fn cosine 70. Oh! I can't solve this because I don't know what Fn is. Oh, I can solve it, can I? No, I can't solve it because I don't know what Fn is. Let's figure out what Fn is. Sum of the forces vertically equals... What's it going to be vertically? Let's do this different colour. What are the forces going to sum to vertically? 0. Because it's not accelerating upwards or downwards. So I'm going to say minus 40 plus, and I'm thinking about this vector, and this vector there is Fn sine 70 plus Fn sine 70 is equal to 0. So Fn is equal to 40 over sine 70. Let's not worry, let's just bung that into that upper equation. Sorry, let's do this. So I'm going to turn around and say v squared is equal to 5 over 4. Rather than Fn, I'm going to put 40 over sine 70. And then we have cosine 70. And you can just work that out, actually. You don't need to do anything special trig thing. So you go, let's do this, 5 times 40, enter. And then times cosine 70, enter. Divided by 4, enter. And here's the thing that people slip off on. Divided by sine 70, enter. And I'm getting 18.2. So that equals 18.2. And so v is equal to the square root of 18.2, which equals second square root, sorry, go back, second square root, go back, second square root, second, oh, I don't have an answer, second square root, 18.25, 18.2, 4.3 basically, 4.266, 4.27. Cool. So those are four examples. So expect one or other. And you know, on this one, I could have asked you for the angle. I could ask you for other things. You know, just because I gave you an example where I'm asking you for velocity, you know, doesn't mean to say I have to ask you for the velocity. I can ask you for different things. Cool? Cool. Cool. And we're just using Newton's second law in this different context. Non-uniform circular motion. Non-uniform circular motion, basically we have acceleration whenever you are going in a circle, and while ever you are going in a circle, you have a centripetal acceleration. That's a given. If you're going in a circle, you have a centripetal acceleration. If you're not speeding up while going in a circle, you don't have a tangential acceleration. But if you are speeding up or you are slowing down while going in a circle, then clearly you also have a tangential acceleration. And all you got to remember is, Pythagoras, we can combine two orthogonal vectors using Pythagoras' equation. So my true acceleration is equal to the vector sum of my centripetal acceleration and my tangential acceleration. So, time t equals 0, a 3 kilogram particle travels at 8 meters per second around a circular path of radius 4 meters. The particle has a tangential acceleration of plus 5 meters. What is the particle's net acceleration? And what is the angle between the particle's net acceleration and the particle's centripetal acceleration? Can you have a go at that for me? Because it is Pythagoras and a little bit of trig. So I'm going to put you on for that. I'm going to pause you. So we're back. So I did this diagram. So the part of it is visualization. It's can you visualize what's going on? And I know that AC is equal to V squared over R because that's our basic equation. So AC must equal 8 squared over 4, which equals what? 64 over 4, which would be something like 16 meters per second squared. And I know that AT is equal to 5 meters per second squared. So I go, well, A is equal to the square root of AC squared plus AT squared. So A is equal to the square root of 16 squared plus 5 squared. AC is equal to, getting my handy dandy calculator, I'm going to go 16.
Coming right up.
Yeah,
okay,
I found some. Be quiet. Sorry, but. So that's going to be 16 squared equals plus 25 equals, so that's going to be, I got 281, square root of 281, so AC is equal to second square root, second answer, and that's going to be 16.76, 16.8 meters per second squared. And then the next thing is, well, what about the direction it goes? What is the particle's net acceleration? And what is the angle between the particle's net acceleration and the particle's centripetal acceleration? So it's that guy that it wants. And I go tan theta is equal to AT over AC. Tan theta is equal to 5 over What's that going to be? AC is, we said, was 16. Tan theta. Well, forget that.
Checking. Okay, I found something on.
I found something too. So AC is equal to, and we go second tangent to the minus 1. 15 divided by 16, close bracket, equals 17.4 degrees.
It's just 5, you said 15.
I said 5. Oh, 5 over 16, yeah, thank you. Is that what you said? Yeah, 5 over 16, thanks.
So as you were plugging it in, you said.
Yeah, I do, yeah, thanks. So, A, yep. So, post-mortem, is your diagram right? Do you have a diagram? That's the first thing. Do you have a diagram? If you don't have a diagram, I'm your coach, and I'm saying you need a diagram. So, do you trust me? And then secondly, if you've got a diagram, is it the right diagram? And if it's not the right diagram, what's wrong about it? So you've got to peel away what's wrong about it, because it's a visualization issue. If it is the right diagram, then do you have the right expression for the centripetal acceleration? If not, then it's learning the equation. If you have the right expression, is it a math slip? Did you get 5? Oh, sorry, did you get 16? Did you do Pythagoras right? Figure out what it was that flummoxed you.
I made 2 diagrams.
So figure out what it was, because that's how you're going to make progress. You're going to see a pattern. You're going to sit around and say, oh, I keep having problems with this. And that's how you really make a pattern. This is another version of this similar type of problem, except here we just have implicitly the knowledge that there's a non-uniform speed. We say a 2 kilogram ball is attached to a branch by a rope that is 4 meters long, so this is 4 meters.
That dotted line is the rope.
Pardon?
That dotted line is the rope.
No, the dotted line is actually just showing a radius. I'm going to visualize this thing with a solid line. The ball is swung in an arc forming a pendulum. Speed of the ball at its lowest point is 7 meters per second. So I've told you where to look. What is the tension in the rope at its lowest point? So we're talking about the lowest point. So I draw it. Tension. V and G. And we're going to apply Newton's laws. Newton's laws vertically. Say the sum of the forces vertically equals. Is there an acceleration vertically? Oh, let's just check on that. It's a good conceptual question. If no acceleration, no ax vert, press A. If you think there's acceleration, yes, ac vert, press B. So let's plug in this. I'm going to ask you why. So look at the diagram. Is there an acceleration vertically? Oh. Fellas, please. So let's go. Let go until a little bit longer. Come on, commit to something. It's either a yes or a no. So come on. And it will be revealing to you whatever you put down. So do you think there's an acceleration in the vertical direction when this mass is like it's been shown? Vertical, yeah. So I'm going to stop you in 3, 2, 1. If I can find my mouse. Stop. Woo! Very interesting. So, I didn't mean to do that. Let's do that again. It just doesn't matter. It'll just start the session again. So let me ask you a question. Is there an acceleration vertically? Oh, that's the question I asked you, isn't it? Is the object going in a circle? Where is the middle of the circle? Vertically above where we're at. So my centripetal acceleration is in that direction. If that's my pivot point, if that's my axis, I always point my centripetal acceleration towards the axis. So there is a vertical acceleration. Just not obvious. Sum of the forces vertically equals ma, which equals mac, which equals mv squared over r. So now, of course, now life's not so bad at all, because I know that this is a 20 Newton force. And so I say, oh, just follow your diagram. You say plus t.
Who would you like?
Why does that keep going off?
Don't know. Plus t added to minus 20. They're my two vertical forces. Is equal to the mass, which is 2, times a, which is my AC, which equals 2 times 7 squared over 4. So t plus minus 20 is equal to 49. A half of 49 is 24.5. So t is equal to 24.5 plus 20. So t is equal to 44.5 newtons.
That was an easy one.
Let's think conceptually for a minute. If it was just hanging there, what would the tension be? Not swinging, just hanging there, what would the tension be?
The normal force.
20 newtons. It's also going in a circle. So the tension has to do two jobs. It has to support the weight and it has to supply the tension to provide the centripetal acceleration. So can you see? It's supporting the weight, it's provided the centripetal acceleration. Two jobs. It's tempting to try and analyze it that way and say, oh yeah, we've got one job which is the weight and one job is the centripetal acceleration. My advice is don't go there. Draw yourself a good diagram, a good free body diagram. Ask yourself, is it in equilibrium or is it not? If it's not in equilibrium, apply Newton's second law and just have faith in the math. Do the diagram right, do the physics right, let the math take care of itself. And it makes it much simpler. Cool. I'm going to break there and we're going to take a quick break. So